Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will further look at our classification workflow that we started building on in the previous lecture. Just as a recap, what we did in the last lecture, we set up our classification problem, which is predicting handwritten digits within our MNIST database. We obtained the data, we visualized the data, we did very simple preparation of data before fitting a simple classification model. This model gave high accuracy, but we wanted to see whether this is good enough, whether accuracy is good enough as a performance metric. So we defined a few alternative performance metrics, and we defined what is referred to as a confusion matrix. But the confusion matrix is only the beginning of beginning of defining alternative performance metrics. So we will look at more on those performance metrics in this lecture. We will also look at a few other ways of performing classification other than just binary classification in this lecture. So as mentioned before, the schematics that I will be using in this slides are taken from this textbook by Aurélien Geron unless otherwise mentioned. Okay. So we looked at the confusion matrix, which has a combination of true positives, false positives, true negatives and false negatives, and within those confusion matrices we can define two powerful performance metrics. So one is referred to as precision, which is the ratio of true positives divided by the total number of positive predictions that you actually make, right, and the second is recall, which is the ratio of true positives divided by the true positives and false negative predictions that you actually make. Recall is also sometimes referred to as sensitivity or true positive rate or TPR, right. Precision and recall are both very useful ways of quantifying the performance of classification models. So one trivial example of a model with perfect precision is that it just makes one single true positive prediction and the rest are all negative predictions, right. So that will be a model which has perfect precision, but will also have very poor recall because it may have made a lot of false negative predictions here. So if you were to look at this confusion matrix here, so let us say some of the predictions are true negatives, some of them are true positives, some are false positives and false negatives. Again, this is the transpose of the confusion matrix that was introduced in the last lecture, but this is the typical confusion matrix that you will get in scikit-learn, right. So in order to calculate precision, you basically take the total number of true positive predictions divided by the total number of positive predictions there is. So in this case you have 3 true positive predictions, 1 false positive prediction, so the precision is 75%, so it is 3 out of 4. So precision is calculated along this axis here, right, whereas recall is calculated along this axis here. So it is the total number of true positive predictions divided by the total number of true positives and false negative predictions. So how many totally true predictions you have, right, or how many totally correct predictions you have, right. So here you have 3 divided by 5, so you have 2 false negatives, so 3 divided by 5, so you have recall of about 60%. Precision and recall are useful metrics because it is impossible to construct a classification model that has both perfect precision as well as perfect recall. In other words, you will always have a trade off whenever you construct a classification model between precision and recall. So you either have models with high precision or you have models with high recall, right. So the way to understand this trade off is to understand that when you create classification models, you create what is referred to as a decision function, right. So think of this as a kind of a threshold value that the model learns. So if a predicted value is above this threshold, then the model generally assigns that as a true prediction or a true value, and if the predicted value is below this threshold, then the model generally tends to assign that as a false prediction or false value, right. So this threshold is what the model is trying to learn, right. So let us say you have a series of numbers here and your model learns this threshold here in the middle, right. So above this threshold are all sort of true predictions and below this threshold are all false predictions by the model. The actual values may be different, right. So let us say you pick up this decision threshold, and let us consider what precision and recall we have, right. So if we take this as a threshold, precision is number of true predictions, so that is 4 true predictions we have, true positives, divided by the number of true positives and number of false positives, number of false positives here. So there is one false positive, which is 6 is being classified as a 5 here, right. So number of true positives are 4, 1 2 3 4, number of false positives is 1. So the ratio of precision is basically 4 by 5 or 80%, right. So if you take this decision threshold, right, you have an 80% precision in your model, and same thing if you were to calculate recall. So for recall, number of false negatives are important. So there is one false negative here and there is another false negative here, right. So these are actually 5s, but the model is classifying them as not 5s, right. So these are false negatives, and then there are 4 true positives. So you have a recall value of 4 divided by 6, right, which is about 67%, right. Let us say you now increase your threshold of your decision function to much higher values, right. So only predictions above this, so if you have threshold values above this, the model predicts it to be positive, below this it predicts it to be negative or false, right. So if you were to increase the threshold, right, you see that the number of true positive predictions are 3, there are no false positive predictions here, right. So the precision actually goes up to 100%, right. So you have a very precise model, but look at the recall, right. So you have 3 true positive predictions, but you are also increasing the number of false positive predictions. So previously you had 2 false positive predictions, you have added 1 more there, right. So the recall actually drops to 50% from 67%, right. So as precision increases, your recall actually drops, right. The vice versa is also true. So if you were to decrease the this decision threshold to a lower value, right, and look at the number of true and false positives here, right. So you have the number of true positives is 6, the number of false positives also increases. Previously you had only one false positive, now you have introduced one more. So the precision is actually 6 by 8 or 75%, which is a drop from the original decision threshold. So the precision actually goes down from 80 to 75%. But if you look at recall, you have minimized the total number of false negative predictions, right. So there are no more false negative predictions. So if you look at all the negative predictions, these are true negatives, right, there are no false negative predictions, all the positive predictions are being captured, right. So the recall now has a value of 6 by 6, right. So all the true positives are captured, there are no false negative predictions, so the recall is 100%. So the recall has actually gone up from the original threshold value, the recall has gone up with the decrease in the threshold to 100%, but the precision has gone down to 75%. So whenever your precision increases, your recall decreases, and vice versa, whenever your recall increases, your precision will decrease, right. So you can also look at this graphically. So I am plotting the variation of precision, which is the blue line here, and recall, which is the green line here, as a function of the threshold function itself for a simple classification model. And you see that as precision starts to rise, the recall starts to drop, right. So what we typically do is we try to identify a model which has some amount of precision. So let us say you want a model that has at least 90% precision, right. You can also evaluate for that model how much recall you have, right, and if that recall is too low, then you may have to modify your decision threshold till you achieve an optimal kind of value, right. And this is a trade off which requires lot of human intervention, right, because we need to make a decision whether our model requires high precision or our models require high trade offs. And just to give you an example of how this precision recall trade off comes into picture, let us say you are designing a model for age restricted content, right. So this could be something like a YouTube or Instagram feed, right. So if you do not want age restricted content to appear, right, for users, then you need a model with very high precision, right. So you definitely want to keep only safe content, right. So you want to minimize false positives as much as possible, right. It is okay to reject safe content as unsafe, right, but it is not advisable to show any unsafe content mistakenly labeled as safe, right. So for age restricted content, you would want a classification model which has very high precision and low recall is okay, right. It is okay to let go of some content which is safe but is classified as unsafe, right. So you want models with high precision here. But let us say you are designing a model for shoplifted detection, right. So let us say this is based out of once again video images, and you want to see whether shoplifting has done or not. So whether someone has stolen an item from your from your shop or not, right. In this case it is okay for you to subject your customers to additional checks. So just to ensure that there is no shoplifting happening, right. Rather than letting go of customers successfully with shoplifted items. So in other words, as a shop you would want to minimize your losses. So if someone is successfully able to steal something out of your shop, then you have a monetary loss, right. So you want preferably all shoplifters getting caught, and some customers who are actually not shoplifters, maybe they are put through some additional checks. So some false alarms are okay, but you want to minimize any kind of false negatives, right. So you want to minimize losses altogether. So in such scenarios you would want to design models with very high recall, low precision is okay. So normal customers can be put to additional checks, but you want to catch any shoplifter possible so that you minimize your monetary losses, right. So you see that different applications will require different choices, right. So in some cases you want high precision, in some cases you want high recall, and in cases where you want models to have a balance, so where you want similar precision values and similar recall values, you can actually define a new performance metric called the F1 score. So the F1 score is very simply the harmonic mean of your precision and recall values, right. So since it is defined as the harmonic mean, if you try to maximize your F1 score, it tries to both sort of have similar values of precision and recall. If you have similar values of precision and recall here, you naturally see that the F1 score sort of maximizes, right. So if you maximize your F1 score, you try to achieve a model which has similar values of both precision and recall. But once again, this may or may not be good for your end application, but this is something that as humans have to take a decision whether we want high precision or high recall, okay. So apart from precision, recall and F1 score, another popular performance measurement metric that is often used is what is referred to as receiver operating characteristic, or ROC curves or ROC plots. So this is usually a visual plot. It plots your true positive rate, also referred to as recall, versus false positive rate, right. So what is false positive rate? It is the negative, or 1 minus the negative of specificity. Specificity is also referred to as true negative rate. So how many true negative predictions does your model actually make? So if you subtract your true negative rate from 1, you basically get your false positive rate. So in other words, you can think of this as plotting your sensitivity versus 1 minus specificity. But the important metric is this. So when you plot an ROC curve, you are looking at area under the ROC curve, and if your model has a value as close to 1, the area under the ROC curve is, if it is as close to 1 as possible, then the model is performing very well. So a perfect classification model will have a area under the ROC curve as 1, and a highly imperfect model will have a area as close to 0. Okay. So let us go back to our notebook and let us look at some of these performance determining metrics. Okay. So we are continuing with our existing notebook here, where we have already downloaded the MNIST dataset, and we even calculated our confusion matrix, right. Let us now see how to calculate our precision and recall values. So once again, to calculate those, we can use this scikit-learn.metrics module, and that has two functions. One is precision score for calculating precision, and the other is recall score for calculating recall, right. Both the functions have very simple syntaxes. So precision score has a syntax of the target value, which is ytrain 5 here, and the prediction values here, right. So the first argument is your target value, the second argument is your prediction values, and we see that the model that we just trained has a prediction a precision value of about 0.83 or 0.84 if we round off, right. So which is pretty decent. We can also check manually whether the precision score function is accurately calculating the precision itself. So we already defined the confusion matrix, which is a simple NumPy array. So we can also calculate the precision by this simple mathematical operation, and we see that the precision values are identical. We can also calculate the recall score. So we see that the recall is a little low, it's about 0.65 or 65%, which is expected. So if you have high precision, you are expected to have lower recalls. We can also check whether the recall score has been calculated correctly, and we see that it has been calculated correctly. We can also calculate the FN score for this model, and the FN score is about 0.73. So if you try to increase the FN score further, the model will try to decrease the precision and increase the recall, so that both are fairly similar. And we can also check whether the FN score has been calculated correctly for this model, and indeed the FN score has been calculated correctly. Okay. Now let us try to understand the precision recall trade off for the model that we had just trained. So we will use our stochastic gradient descent classification model, right, and let us look at some. So if you take this classification model, in order to understand what the threshold value is, there is this inbuilt function called a decision function, right. So the decision function basically tells you what kind of threshold values it calculated for each of the data points that you actually provide as arguments within that decision function, right. So for example, in this function we have given 2 data points. So one is the 35,000th data point, and the other is the 30,000th data point, and it actually gives you what kind of scores it calculated, what kind of threshold scores it calculated. So in one case it calculated a threshold of negative 2800, in the other case it calculated a score of negative 5300, right. Okay, so those are the kind of decision scores or decision values it actually calculates. So the way the model works is, so it calculates these decision values. If they are below a certain threshold, then the model sets them as false. If they are above this threshold, the model sets them as true, right. So that is how all binary classification models work. Let us now set a fairly artificially low threshold value of negative 13,000. Right. So we saw that in the previous block the calculated values were about 2800, 5300 negative, right. So if we set a very low threshold of negative 13,000, let us see what kind of predictions we get. We get the predictions to be true now, right, and if we set very high thresholds, we get the predictions to be false, right. So this sort of makes sense. So if your threshold is very high, all your predictions will generally turn out to be false. If your threshold is very low, all your predictions will generally turn out to be true. Higher thresholds generally give rise to high precisions, lower thresholds generally give rise to high recall. Okay. Let us now get these scores in a fairly cross validated fashion, and let us try to plot how the precision and recall values are varying as a function of these threshold values, right. So let us try to do that exercise. So as the so whenever you do cross validation, right, so the models will take more time to execute because you have different slices of data and the model is actually learning through those slices. So this code block will take a few seconds to complete, and it is done now. So we then once the model has learned via cross validation, we get a set of scores from we get a set of target values from the model, and then we define or we import this function called the precision recall curve, which helps us plot this variation of precision as well as recall as a function of threshold. So we can actually get all of these values in one shot. So what precisions we get, what recall values we get corresponding to the threshold values that the function actually chooses, right. And then this code block here basically defines a very simple plotting function to plot this variation. So I have just executed that code block here, and the results are below, right. So you see that the precision has been plotted in blue and the recall has been plotted in green as a function of the threshold value. The red line basically indicates what is the threshold you need if you were to have a 90% precision, right, and the recall value is also listed here. So the recall value is I think about 45 or 46%, the precision is about 90%, right. So you clearly see an example where as you keep varying the threshold, your precision changes and your recall also changes, but both change in the opposite direction, okay. We can also plot the change in precision as a function of recall itself, right. So both are sort of dependent variables, both of them depend on the threshold itself. So we can also actually plot how precision varies as a function of recall, and that plot is shown here. So you see that at high values of precision you have low values of recall, and as recall keeps increasing you see the precision first gradually decreasing and then it sort of tanks towards the end. And when you have about 90% precision, that corresponding recall is about 45% or so, okay. And just to numerically check what the threshold value is, so the threshold value at 90% precision within our model is about 3300, and just manually checking whether the if we set the same threshold values that we had calculated before, if we manually set that threshold value, are we getting the right precision? Turns out yes, about 0.9, and the recall value is about 0.479, right, okay. So that is to understand the variation between precision and recall and the trade off. Let us now look at the ROC curve, right. So in order to plotting the ROC curve is again fairly simple. So there is a standard function that is available, and that function again takes the actual values, actual y values and the predicted y values, right. And I have defined this simple function for plotting the ROC curve, and as you see it plots your recall versus 1 minus specificity here. There is a dashed black line which is basically your parity line. So in general you want your models to lie above the parity line at least, right, because below the parity line the area under the curve is less than 0.5, so above the parity line you can at least get higher areas, and we see that for our model it's quite decent, right. So it is hugging the y axis as much as possible when you have low values of 1 minus specificity, and it is sort of approaching the y limit or the x axis at y equals 1 as you start approaching high values of recall, right. And this red dot basically indicates what is the value of recall when we set our precision to be 90%. So it was about 0.4479, so that is the value that is listed here. Let us now look at the score also, the area under the curve, which is so in order to calculate the area under the curve for the ROC curve, there is a very simple score function that you can import, and you see that the area under the curve is about 96%, so 0.96, which is fairly decent for a classification model. So we see that our classification model is actually doing a reasonably good job, even if our model is simple. So we initially started with accuracy, we were little skeptical because the accuracy was already high and it is very easy to get high accuracies within this data set. So that is why we looked at other performance measurement metrics, and looks like the model is quite decent after all. I am going to start executing the few code blocks that are following, because these will take time. So I will just start executing them and then we will go back to our slides. Okay. Let us go back to our slides. So the other parts of the workflow are fairly straightforward. So you can prepare data for machine learning, which we have already done, so we do not need to do much for this classification exercise. You can select a model and train. So we tried it with the SGD classifier, it seems fairly good, right. There are also other models that you can try out. You can try out a decision tree classifier, you can try out random forest, you can try out support vector machine and so on. All of the models that we tried out for regression, they have corresponding classification models as well. And the next step would be to fine tune our model, do hyperparameter optimization either through grid search or randomized search, and then the final step would be to present or deploy the final model, right. So we will actually skip all these steps because these are fairly straightforward to do. So you take the same sort of code blocks from your regression exercises and you execute them for your classification counterpart, right. So these steps are fairly straightforward, so we will skip those in terms of exercises on our notebook. And then we will focus more on other types of classification. So with classification so far we looked at what is referred to as a binary classification, right. So when the model is presented an image, we are either classifying that as a 5 or not 5, right. So the model produces only one value, it outputs one value and it is binary in nature, 5 or not 5, right. We can also build what is referred to as a multi-class classification model, right. So in our data set, in our MNIST data set, we have 10 different digits, right. So from 0 all the way to 9, right. So in principle we want our classification model to output whether the number is 0 or the number is 1 or the number is 2 and so on. So we do not want our model to just say whether it is 0 or not 0, we also, if it is not 0, we also want our model to say whether it is 3 or a 4 or a 5, right. So if we build a classification model which can output one of a discrete set of labels, a discrete finite set of labels, then that is referred to as a multi-class classification model. There are multiple multi-class classification models that exist. So stochastic gradient descent, random forest, these are all classification models that are out there which can directly do this multi-class classification, right. So if you provide these models with multiple target values, they will automatically do multi-class classification. They will try to predict for each data point, they will try to predict one of the different classes that you have already exposed to the model during training. For few of the other classification models, we may have to construct multiple binary classifiers and which will then help them to do multi-class classification, right. So in terms of multi-class classification in general, models choose one of these two strategies. So one is referred to as one versus rest, which is the typical strategy that is often used by most models. Other is the one versus one strategy. This is used by models which are often dealing with small data sets. So let us say you only have few hundred or few thousand data points, then you may have to use one versus one rather than one versus rest, right. So what does one versus rest do? So here the models train 10 different detectors. So for example you have 10 different digits here, right. So your model will train a detector for 0, so it will try to classify an incoming digit as 0 or not 0, 1 or not 1, 2 or not 2, 3 or not 3 and so on. So it will train 10 different detectors, 10 different binary classifiers, and for any new data it will pick the detector that outputs the highest score, right. So let us say you show an image of 5 to a model, the 0 detector will output a score, the 1 detector will output a score, 2 detector will output a score and so on, and the model will pick whichever detector outputs the highest score. So if the detector 5 outputs the highest score, then the model will detect that image as 5, whereas if the detector 3 output the highest score, then it will falsely detect that image as a 3 and so on, right. So that is one versus rest strategy. So here the number of models that are being trained is 10, right. So and among the 10 you choose whichever model, for any new data point you choose whichever model gives you the best prediction, right. One versus one is slightly more complicated. So here you actually do several combinations of binary predictions. So for instance we have 10 digits in our data set, so you can now train a binary model to classify whether a digit is 0 or 1, 1 or 2, 2 or 3 and so on. So you actually have 45 possible combinations, right, that you can actually generate, and in fact you actually train 45 different models. So you train models to classify either an incoming image is 0 or 1 or incoming image is 1 or 2 and so on, right. Now among these 45 models, for a new data point you choose once again a model with the highest score, right. Now you may think, okay, this is a very redundant strategy, why would I ever do this, why would I train 45 different models? Well, in models which have let us say you have very small data sets, so let us say you have only 100 data points, 1000 data points and so on, you may actually want to train a lot of different models so that your model learns different possible combinations and learns whichever combination is the most discrete among the lot, right, and it is able to have a higher degree of confidence in its classification exercise than just having 10 models and having 10 binary predictions, right. So in larger data sets where you have tens of thousands, hundreds of thousands, millions of data points, you would use this one versus rest strategy, and in smaller data sets you would use one versus one strategy, right. So often the choice of this strategy is done under the hood. So if you use scikit-learn, depending on the classification model you use, scikit-learn will choose one of these two strategies depending on your dataset size itself. So you do not have to explicitly choose one of these strategies, but you can also treat these as hyperparameters and you can actually try them out, right. So we will not cover the details of how to change, how to go from 1 versus rest to 1 versus 1, we will just look at how to do multi-class classification within our notebook. So let us get back to our notebook. So I executed a few different code blocks already because they would take more time. So for this multi-class classification exercise we will use support vector machine classification. So if you recollect, we also use support vector machines to do our regression, that was one of the models that we tried. So you can use that same machine to also do a classification exercise, that is what we do here. Now I am only taking the first 1000 data points to train this model. So I am actually not taking all the 70,000 data points because it will actually take quite a bit of time. But if you want to try this out, you just remove the colon 1000 within the square brackets from both your x train and y train, then both of them are arrays basically. So if you remove them, you are basically taking the entire data set into account, entire training data set into account, and you will be training your support vector classification model, right. So the model has already been trained, and this gamma here is basically once again a hyperparameter. It helps the model train a little bit faster, right. So if you use fetch underscore openml function, this line of code should work fine. If that did not work, if you use the backup code, then comment out this line and uncomment this line here and execute this line, right. Okay. So we have already trained our support vector machine classification model, and then we want to see how that model makes a prediction in a data point that it does not see. So we will take the 10,000th digit, looks like that digit is 3 here, right, and let us look at what kind of scores the classification model gets, right. So the first value within this array is 0 or 1 classification. So the support vector machine is outputting 10 values here. So it is using 1 versus rest strategy. So it is training 10 different detectors, right. So the first detector is for 0, second is for 1, third is for 2 and so on, and I think the maximum value is 9.19 here, which is probably 7, right. So I do not think the model is getting it right, and let us see if it is indeed true that the model is not getting it right. I think looks like the model is not getting it right, it is actually 7 here. Let me re-execute this, okay. And if you want to try out or if you want to see what are the different classes that the support vector machine is actually classifying, you can see that you can actually use this dot classes variable, and you see that it is actually classifying from 0 all the way to 9 here, right. And the first class is 0, yeah. And we can also train with a slightly larger data set, which is what we have done here, and if we were to execute this model, okay, let me I think there was a variable declaration problem somewhere, so the notebook is taking more time than usual. Okay, so now it stopped. So let me try to re-execute all of these in sequence. Yeah. So you now see that the model actually when we train only on the first 1000 digits, the model did not do well. So it only it misclassified it as 7 instead of a 3. So the final 4 sort of code blocks here basically increases the amount of data in the training process, and with more data you should see that the model is getting things better. I think it is indeed getting better. Yeah, so with more training data you see that the highest score is, so the first value is 0, second value is 1, third value is 2 and fourth value is for 3. You see that for the same digit the model is now getting it right. So it is able to predict it as a 3 and not a 7, right. We can also calculate what is the cross validation score for this model. So we are doing 3-fold cross validation here and we are measuring accuracy. One way to sort of trivially improve the accuracy of these classification models is to have a very simple scaling of your data. So our data is all 0 to 255 numerical values, right, within a 28 by 28 grid. So we can do a simple standardization, right, and if we do standardization you will see that the model scores actually improve, right. So we will come back to these, so these may take a little more time. So we can come back to these after going through multi-label classification. Okay. So we looked at multi-class classification. So we can also construct classification models that can predict multiple labels. So what do I mean by that? So for each data point there can be multiple categories for the data point where the model is predicting either true or false, right. So think of it as multiple true or false predictions for each data point. So the multi-classes, there are multiple classes, the data point is fitting into one of those classes. So the prediction is still 1, there is only one output. Here in a multi-label classification there can be multiple predictions, there can be multiple outputs. So the classic example is let us say you upload a group photo on your Facebook or Instagram, right, and let us say you have a facial recognition algorithm, for the same photo the algorithm can recognize multiple faces within your photo, right, depending on your friends list, right. That is an example of multi-label classification. So if you upload a photo with just your face, the algorithm will only recognize you. If you upload let us say a group of 10 where 5 of them are your friends on Facebook or Instagram, then the algorithm will actually make predictions for all the 10 with one value being for you and the remaining 5 of your friends will also be classified as true, right, and the other people will not be recognized, right. So it can actually make multiple labels or multiple predictions. So in our case, right, so in our data set we are going to create 2 labels. One is whether a digit is large or not, so whether or not you have greater than 7, right, and the other is whether the digit is odd, right. So for each image instead of making just one prediction whether it is 0 to 9 we are going to make 2 predictions, right. So our 2 labels, 2 targets. So one is whether the digit that we are exposing the model is a large digit, so whether it is greater than or equal to 7, and whether it is an odd digit, right, so whether it is 1, 3, 5, 7 or 9, right. And for this multi-label exercise we are going to use a different classification model called k nearest neighbors. Once again we will go through the details a little later. So let us go back to our notebook and execute a simple multi-label classification task. Okay. So I think the cross validation from our multi-class classification is still executing. So let me stop it because I think this may not run on time, and let us go to multi-label classification. This may actually run quicker. So the way multi-label classification works is again fairly simple. So we import this k neighbors classifier class. We have to introduce the new target variables, right, target labels. So we introduce one label as y train large here and the other label as y train odd here. So we have now introduced 2 labels, right, and then we stack them as a 2 columned target array. So classically whenever we fit our machine learning models we had one vector of targets, now we have an array of targets, so we have 2 columns, right. So that is what this stacking line does, y underscore multi label. And then let's so we are plotting a digit here, so some digit is again a 3, so we will see whether the model is correctly predicting 3 to be a small number and an odd number, right. So we fit our model, so we create an instance of the model and then we fit our model. So fitting is again the same x comma y kind of syntax, and then we make a prediction on that digit and it looks like the model is predicting this to be not a large integer, which is correct, and an odd integer, which is also correct. So the multi-label classification seems to work fine. Okay. Let us now go back to our slides and look at the final way of classification, which is referred to as a multi-output classification, right. So what is a multi-output classification? It is basically combining both a multi-class and a multi-label, right. So classic example is for any image recognition, right. So let us say if we take our own MNIST database, right. So we have for each pixel we can have an output between 0 to 255, right. So this is our grayscale, right. So for each pixel you can have one of these values, one of 0 to 255, but then each image has multiple pixels, right. So you also need to give multiple predictions for each image, right. So if you want to reproduce an image, right. So let us say you have a noisy image and you want to reproduce or reconstruct an original image. For each pixel you have to make a prediction and you have to make predictions for multiple pixels. So for each pixel you are doing a multi-class classification, and for each image you are predicting multiple pixels, so that is a multi-label classification. So when you do both of them combined, right, that is referred to as multi-output classification. So we will take the example of recovering image from recovering the true image from a noisy image within our MNIST dataset itself, right. So let us get back to our notebook. And let us do simple multi-output classification, and for this multi-output classification we will use our k nearest neighbor classification model itself. So the first code block basically adds noise to our image. So you see that the image is now more noisy than the original image, right. So that is what we are doing here. So we are basically defining a random noise and then adding that to our image, right. And then we are keeping track of at least one image. We want to see how the model is performing for one image. So we have basically converted a clean 4, an image of 4, to a noisy image of 4, and let us now train a classification model, the k nearest neighbor classification model, and this model should ideally make a multi-output prediction. So we are training it on noisy images, and now it should ideally be able to recover back the original image of a clean 4. And let us see if the model has done that, and we see that yes, indeed the model has reconstructed the original image. So we fed it the noisy image, right, and it has reconstructed the original image of 4 after training, right. So this is an example of a multi-output classification task. So let us now go back to our slides and let us summarize in two parts. So first is we will summarize some of the important functions and classes that we covered as part of this classification workflow. Cross validation predict, this is a new function that we introduced which is different from cross validation score, right, which is commonly used in regression. This is more useful in classification. We introduced new performance metrics, confusion matrix, precision, recall, F1 score here, and also ROC curve and recall curve, precision recall curve and ROC curve. All of these are available in scikit-learn metrics, right. And for classification models also, for each model we use the same functions, so fit and predict compared to regression. With that, let us summarize what we learnt in this lecture. So we once again started out with our classification problem. We executed binary classification, we defined new performance metrics, accuracy is what we classically used, we defined new metrics precision, recall, and we understood how precision and recall have an intrinsic trade off. So you cannot have a classification model that is simultaneously good at precision as well as recall. We also looked at other ways of building classification. So multi-class classification where the model makes one prediction but not binary. So it can make one out of several classes, right. So 0 all the way to 9 for example. We can also do multi-label predictions. So here the model simultaneously for one data point it makes multiple target predictions, right, and multi-output basically combines multi-class and multi-labels, right. So for multi-class we looked at generalizing the model from predicting just 5 or not 5 to 0 to 9. For multi-label we looked at whether the model can predict both whether a number is large as well as odd, and for multi-output we reconstructed our original image from a noisy image, right. So these are all types of classifications that are quite commonly done, and for multi-class classification there are two strategies that are commonly employed, one versus rest and one versus one. Normally we do not have to worry about it because scikit-learn chooses this automatically whenever we do multi-class classification, but it is important to know the trade offs between these two, and there are ways that we can restrict ourselves to do either one versus rest or one versus one strategies, right. So in the next lecture we will do some of our hands-on sessions, right, and we will also construct or we will also understand how some of the classical machine learning models work. So we will understand some of the nitty-gritties within those classical machine learning models, a little bit of the math, little bit of the algorithms and so on. With that I thank you all for joining this lecture. I will see you all in the next one.